Although I was announced as an engineer with 35 years of experience, I will be talking about things which are completely new to me. And neural networks are not really my application, let's say, field until now. So it will be a little bit like a beginner's approach to the problem. Will be very basic, but I hope that probably most of you are already experts in neural networks, so it's a very inconvenient situation for me. But could be some still who are not really, let's say, experts in this or can learn something more. I will be presenting this on behalf of our group, where the other names, Christian, Alan, and Torsten, are physicists and specialists in neural networks. I am an application engineer and would like to apply these methods according to their specifications. Okay, so first let's talk about the application field. Most of you are probably connected to CERN and these accelerator-based experiments. This is not an accelerator-based experiment. This is a cosmic ray experiment. We are looking for ultra-high energy neutrinos, which are coming from very specific phenomena, like, for instance, what happens in vicinity of supermassive black holes, or if two neutrons start merges, and well, there are also other phenomena like gamma ray bursts, which one would like to investigate. Or they produce TeV neutrinos, and only then they can be produced. Neutrinos are good probes because if they reach the Earth, one can be sure that they were not changed by anything. They were not influenced by mass that they traverse and so on. So they still carry the original information. And we can detect the neutrinos. Sometimes, very rare, but sometimes they interact with matter. Then they produce a muon. And muon traverses the media and excites the media. The media, good media, is actually ice. It's dense enough to boost the interaction rate, yet it's media where electromagnetic waves can propagate. And these electromagnetic waves, they actually appear from the fact that muon, which is traversing the media, is actually traversing this faster than the speed of light in this media. And what happens is a cone of shock wave, which is similar to where when a supersonic plane is crossing the sound barrier. So instead of here, the sound wave, we will get electromagnetic wave. And those electromagnetic waves can be detected also by antennas. We were, until now, using optical detectors, but now it will be probably easier to make it with antennas. So, there were already several experiments using this. Was Ariana, Ara. They were all placed at the South Pole. Odd place, but it has lots of ice, and that's a good place. Now there is a detector which is called RNOG, which is placed in Greenland, and this will be like a predecessor for the extension of quite a big experiment which is already at the South Pole, which is called IceCube. And the experiment will contain lots of antennas. It will be several hundreds of antennas. They will be spread on the area of several hundreds square kilometers. So there are two problems with this. First is the power. We should use as little power as possible. The other is that the event rate which we are allowed to send from each station was just 1 Hertz, so 1 event per second. And the signal. You see that the waveform which contains a neutrino signal and some simple noise fluctuation. So how can you detect the thing? You can apply, of course, some levels on analog way, and crossing the level would mean that this is an event. Of course, the noise fluctuation will also do the same, so your data will be probably flooded with just simple noise. You can also apply coincidence trigger, where you require a level crossing by several antennas. You can, within some certain time, you can have a beamforming, where you can, I will be talking about this later, where you have an array of antennas, and by just shifting the phase, you can also detect wave angle. And the last, not least, is a deep learning, and according to simulations, it should substantially prevail over the other methods, also being able to detect a neutrino signal within the noise level. So this is what we are going to do. We are going to implement this algorithm, the deep learning, so neural network algorithm, on already existing board. This board is quite old, and it will be used for the RNO experiment as the predecessor. So we will be able to test the performance. And so far, we would like to use it as a second level trigger, so being pre-triggered by a coincidence trigger or by a beamforming trigger, checking the performance of the neural network. Later, we are going to implement it on a little bit more performant board, and implement it in the South Pole experiment IceCube Generation 2. Maybe worth mentioning is that right now we are targeting a system which is 500 megasample per second, 8-bit ADCs. Later, there will be a board which has 12-bit, 1 gigabit per second. Also here, the deviations when it comes to power consuming and so on, regarding the previous session, here we are having two different boards, one which is like a digitizer board and one which is an FPGA board. Would have been much better to use actually an RF SoC instead, but it's simply too expensive and we need several hundred boards, so it will lead to to big expense, which is not possible. Yes. So we are going to test the results, and for the first stage, we are testing this on the very well-known D1 SoC board from Altera, and then for the Xilinx board in the later stage, I'm using my own board, which contains Xilinx UltraScale Plus chip. In this case, it also offers 60 optical links, but they are irrelevant for the project. So the beamforming trigger, which is implemented on the Flower board, which is this first generation board, which is going to be used in RNOG. It contains, as I said, it contains 4 channel using 500 megasample per second 8-bit ADCs. And The antenna contains 4 sections. So this is a simple array. The antennas will give signals, and then the beamforming trigger is then aligning the phases so that after squaring of the samples, one can see the excess of the power, and this one can put a threshold on and then go on. Now, once it comes the algorithm for the neural network, which is coming up top on the silver plate. I have got it from my colleagues. And this is the structure of the neural network which we are going to use. So we will try to recognize the event, which is the tiny fluctuations from the neutrino, on a sample of 254 samples record. We will be using a number of convoluting stages, which is actually 42 in this case. Then use comparing to 0 to give the necessary nonlinearity, then max pool, and then flatten, and then latest convolution. I have Googled it out and found out that this is a typical structure of a neural network. Lesson number 1 to me. One can see here that one has a convolution of so 5 convolutions per stage, and then the stages are shifted and overlapping. This is one of the possibilities. So 5 multiplications and shift of 2. There has been also other possibilities tested. The more you convolute, the more you overlap, the better results you get. Albeit then you get also more complex structure, which requires more DSPs. And one finds out that actually the performance doesn't really go proportional to the complexity of the hardware. So somewhere there should be some kind of optimum. Mostly it should be at the level of what is actually feasible. So let's try something like this. Now we have 5 convolutions per and then a shift of 3. This is not all, because one has also observed that if one has this multiplied by 5, that means the same, let's say, record is being treated by 5 parallel such structures, then it will give a better result. Okay? Just to believe. One see the following thing. So then one thinks of the speed. Can we manage to, with the incoming data, to get the result with the pace of the incoming data? That means that our processing time is at least a little bit shorter or equal to the time where the data is actually shifted in. So one would like to process this as fast as possible. So one is thinking, okay, that maybe one should do like that. Probably it's on the other page. Yes. Yes. One can think of having, let's say, 5 multiplications made in parallel here, and then a stage of 3 2x2 summing, or should one have one where summing and multiplication goes in series? And what goes in favorite of this kind of multiplication, accumulation, is that, of course, the FPGA DSP is actually providing this structure, so this is a hard structure. It will simply work faster. Okay. Now we have 5 multiplications here, and at the end we have also 5 multiplications here. It would be really well-balanced structure performing with the same pace all the way. Now one can observe one thing. All these values for weights in this multiplication or convolution stage are actually identical for all multipliers, which makes it easy to modularize. Also, that the data which are coming from the ADC, they are coming one by one. So one can start using this data and multiplying as the data are coming. So we do not need to wait for the whole record. We can just start doing this in flight. In here, we would have 5 multiplications to be done, while we have a shift by 3. So we should perform faster with multiplication stages than the data shifted. This is not really a good thing, especially that shifting at 500 megahertz would take just 2 nanoseconds. So we would have 6 nanoseconds. So within 6 nanoseconds, we would have to make 5 multiplications. It will be hard for the Cyclone V. So it's not really a good idea. So one can do like this, that one multiplies this. And now one has 5, let's say, multiplication stages made in parallel, whereas we have a shift S by 6, less multiplication stages than shifts, a little bit better. In the whole counting, one should also have a multiplication time and data sampling period, of course. Data sampling period is 2 nanoseconds. Multiplication time is by now unknown. We only know that from the specifications that it's 400 megahertz maximum time or the minimum time for the multiplication in Cyclone V. All right. So, okay, so we can also put the following structure, make a module, and we have also the last convolution stage, which is called the dancing stage, incorporated. And we have a module which we can actually reuse. So we have 10 multipliers there, and we have 1 multiplier in the blue stage, where this blue multiplier is actually doubled, because I have seen that when it comes to performance, of course, here we have 9 by 9 multipliers, here's 18 by 9 multiplier. It will require some kind of support, so this has been doubled. Okay. Now, if we have a neural network like this, of course 5 and 4 antennas, which we have, what we can do is to check the performance. And then we check it like this. I put some kind of pattern, run the algorithm, and see what is the result. And until the result is repeatable, the same, I can understand that this is performing well. After some, if one is increasing the frequency, the sampling frequency, at a certain moment it simply starts to fail. So then we can see how is it performing. So what I could see is that here is the power consumption, and here is the frequency. I have reached actually 230 megahertz on it, and the power is below 1 watt. So we can say that for the Cyclone V, we have 230 megahertz, which is 4.34 nanoseconds. Now we can see that actually the whole algorithm could work. If we had a structure like that, then it could work online, multiplying and accumulating and getting the result at the pace of the incoming data. That would be this. The Kintex ultrascale I haven't yet tested. This is something which is in red, not valid. I can show you why. Now the problem is that if one is analyzing a record and getting an answer at the end of the record, and then it's another record, and get the answer until the end of the record. Now we also have a problem of what is happening if we have an event here where our algorithm might be insensitive. So of course we need to run this algorithms in interleave mode, which essentially makes the resources which are necessary doubled. So in order to run it online, completely online, without any support of any other pre-trigger, then it would require on the Cyclone V 192 multipliers. We only have 150, so it's not feasible. We can forget about this for the first stage. We can only have, let's say, a pre-triggered version. Whereas on the Kintex ultrascale, running at 250 megahertz, it would, of course, require 384 multipliers out of 1,300 or even excess. So it's definitely feasible inside. And the question is whether we can actually run it at double the speed, 500 megahertz. This is something which one can check. But this will be later this week or the next week. We can check it. Now, I have implemented this algorithm completely without any concern of how the multiplier is actually made. This is actually tempting to say A gets A plus B times C. That's simple. And this is how it was done. So we are omitting the whole structure. The features of registering inputs, outputs, we are just omitting this completely here in this project. Okay, and it could be also an interesting bunch of results. Look at how fast are actually the multipliers in the Kintex ultrascale Plus and also Cyclone V. So what one can do? One can have a timer which is saying now, and a coefficient modifier, modify two coefficients. Now the two coefficients are entering a serial chain of multipliers, where one coefficient is actually constant, the other coefficient comes as a result of the multiplication. And it propagates. So what we are expecting that after changing a coefficient, somewhere here, we have the result, which is getting sampled and then put into a signal tap, in this case, and we will get some intermediate evaluation until it stabilizes and we have the result. And then we calculate how many stages or how many clock samples it needed for stabilization. And then we say, okay, now it's stable. 160 nanoseconds it took, 8 samples, 20 nanoseconds each, divided by 64 multipliers which were in the chain. That's 2.5 nanoseconds, and it's really in according to the book. So 400 megahertz it should have taken. One can also check how much power does it take, and I got 0.72 watt. which, given that we are working at 400 megahertz here, and that the duty cycle of that is only half, we get something like 50 microwatt per megahertz. It does not need to be linear. It's at the end probably somewhere. But that's an indication. A very similar experiment using Xilinx gives for 64 multipliers a latency of 60 nanoseconds. So 160 in Cyclone V, here is 60. That's the difference. And this is, again, consistent with the specification, which says that the multiplier is actually working alone without constraints at 1 gigahertz. And the power consumption, here I have arrived at 20 microwatt per megahertz. So this is the gain which one gets when one goes from 28 nanometers of the Cyclone V to 16 nanometers of the Kintex UltraScale Plus. Okay, so this is what we wanted to have. We wanted to have some working, let's say, prototype, which is scalable, of the neural network trigger. We have performed feasibility studies for these two experiments when it comes to the speed, performance, and power consumption. So we can then draw conclusions which way to go. Yeah, as I said, we have used these two boards, which are, one of them is available, another one, definitely you can find an evaluation board for that. And the last statement is that this is practically written in a platform-independent VHDL, apart from the PLL section, which is boosting the frequency for the experiment, and also the memories, which, of course, the memories one can implement in VHDL and let it be, let's say, occupying the whole structure with it, or one can specifically say and also instantiate a proper memory block in each of the Altera and Xilinx. So that was it. Thank you.
Thank you, Pavel. Any questions?
Thank you for the great presentation. I just wanted to understand, like the previous presentation, you have a use case where you need to use an FPGA platform, right? An RF-based FPGA platform, right? And you have issues with power, right? And you have issues with the cost, right? And now you are trying to optimize them on the algorithm basis, how on your design in order to compensate for that, right? And you also showed that when you went to lower nanometer rate, right, you saw quite a gain in the performance also. So don't you think for a project of this magnitude that you can move and go for a custom ASIC rather than sticking up with FPGA and looking for that? Because in the long run, the power consumption and all would be better on that kind of a platform.
I did not understand. Going with what?
With an ASIC, a custom ASIC for your use case.
Yeah, an ASIC would be a perfect thing, but I am not an expert in ASIC, and I can understand that the ASIC development will take quite a long time. We have this time, in principle, we have some 7, maybe realistically saying years, and also that the making of the ASIC could be expensive, just the prototyping. So we haven't thought about this, but that's a good.
How many of these processors you have in the end?
I guess it will be 200 or 300 stations. I don't have the exact number.
Okay. I think there was a question over there. Yes.
Yeah, just one question regarding the neural network itself. How did you train the neural network, and what is the gain compared to the other algorithm?
Yes, I have not trained to answer this. It was trained by 2 other colleagues, by Alan and Torsten. And they have checked it. They have checked it also for different other configurations. And there are graphs also showing the performance versus configuration. I am not, let's say, an expert in this. But I can just trust, given the whole structure on, let's say, silver plate.
Hello. Just to follow on it, what is the tool that was chosen? Do you know if it's TensorFlow or PyTorch, or how did you come to the coefficient? How did they come to the coefficient, and how did you transfer the architecture from what they made to your CNN?
No, I cannot answer what was the tool for training or for whatever. What I have got, of course, were weights, and the weights were, of course, also a double precision. So it's like, one needs to check the dynamic range of those weights and define whether one should use a floating point or not. I found the dynamic range to be 500, which is not really pointing for a floating point. One can easily implement it using even 9-bit. So I have simply shrinked it, and my colleague will then. Let's say, their task would be now to see what will be the degradation of performance with this already quantized to 500 values. And that would be it.
Hello, thank you. One short question. Which tool did you use to convert the model to VHDL, or did you write the VHDL by hand?
It's pure VHDL. No tool other than Vivado and Quartus.
So I was referring to tools such as HLS4ML or Fin or some other. Okay.
No, nothing like this. For 2 reasons. First of all, that I'm a complete newbie, and I don't know other tools. That I can confess. The other thing is that one can be also afraid of that every tool which is of a high level may also introduce some one could say overhead, which is not really needed. It will be just power consuming and probably will not be optimal. That there are two ways. And the third is just to explore the thing from the very ground.
Okay, thank you.
Okay, I think we have to move on. Oh, you have a question. Just because it's you.
It's very quick, actually. So for the power estimation you showed, is this estimation or you actually measure on the flower board you have?
I have measured.
So you measure it. Oh, does it include the dynamic power?
No, not on the flower board.
Okay,
I said it was on the SoC,
okay.
Which also contains a Cyclone V.
Okay, okay.
So it's like the other one. There is a slight difference, of course, between the flower and this one, but I don't think that the power consumption would be actually different.
Right, doesn't include dynamic power, so you actually run through like a realistic data.
So I just, what one can do is just to measure the power consumption when one resets the whole stuff, nothing is moving, let's say, and then remove the reset, let it run. That's it.
I see. Okay, thank you.
Thank you. So let's thank the speaker again.